So let's dive into our first u-substitution exact example. So we're given the integral of the square root of the quantity 2x plus 1 dx. And we want to use u-substitution to evaluate this integral. So the first thing we'll need to do is we'll need to locate u, and that's got to be f of x. So here's a good question that we're going to ask ourselves when we're trying to find what should be u. What is being operated on? Since we know that f of x most usually is going to be raised to a power of n, then whatever the function is that is being operated on is usually, not always, but is usually a good choice for u. So if I was to rewrite this integral, it would be the integral of 2x plus 1, and it's being raised to the power of 1/2. So what's being operated on here, which would be a good choice for u, or my first natural choice for u, is the function 2x plus 1. So I'm going to pick the expression that I want for u, and then I'm going to find du dx. Because again, I'm after completely rewriting this integral in terms of u, and I need to evaluate that with respect to u, so I need u and du inside that integral. So here's the point where I ignore the integral. I don't care what's up there. I'm only looking at my choice for u. And the derivative of that is 2. But now I don't want the derivative. I'm not going to put du dx in this integral. I only want du in the integral. So I need to solve this for the differential du. And I can do that algebraically by multiplying dx on both sides. And it is true that in the context of u-substitution, those are going to cancel. So du is going to be equivalent to 2 times dx. So what I'm after is I want to completely rewrite the original integral, which was 2x plus 1 to the 1/2 dx, totally and completely in terms of u and du. Well, u, I said, was 2x plus 1, and that's being raised to the power of 1/2. du is 2x. So now I have this completely rewritten as u to the 1/2. Well, all I have left is 1 dx. I don't have 2 dx's, so I have a problem. How can I write the with respect to so that this is a true statement? This is important. It needs to be the same value. It just needs to look different. So isn't it true that dx would have to be 1/2 of du? That's a true statement that leads from this relationship. And if that's true, instead of writing just du here, I'm going to write 1/2 of du there. All right, hopefully you can follow that. I'm going to rewrite this here. So now I have the integral of u to the 1/2 times 1/2 du. And now all of this is multiplication. That's multiplication, that's multiplication. So multiplication is commutative. I can write this in any order that I want to. 1/2 times u to the 1/2 times du is equivalent. And just as we've always said, when dealing with these indefinite integrals, constants can pop out front. So this is how I would equivalently write this integrand. Now I'm going to go on to the next screen, and we've got the whole lookout thing. And here, if you'll look at this really quickly, this is exactly what we had on the prior slide. We said that if u is 2x plus 1 and du is 2 dx, then I can equivalently write that original integral like so. And I want to prove to you that I can, because I want to put this totally back in terms of x and dx and show you that it's equal. Well, again, constants pop out front, so I'm just writing that down. And now here's my integral. I have u raised to the 1/2. We said u was 2x plus 1. And now I have du. And here we said du was 2 dx. And look what happens for me. That 2 cancels with that 1/2. And when I clean this up, sure enough, it is equivalent. When I back substitute in terms of the original variable, it's equivalent to the original integrand or integral that they gave me. And now I have totally simplified that integral. And I've simplified it so that it looks like the integral, this is where we were, 1/2 times the integral of u to the 1/2 du. Now I'm going to use the power rule. I'm going to actually find the antiderivative function. My constants pop out front. I have 1 over n plus 1, u to the n plus 1 plus c. So this is 1/2 times 1 over 3/2, that's a 3, u to the 3/2 plus c. We'll clean it up one more step. 1/2. 1 over 3/2 is 2/3. U to the 3/2 plus c. This is just algebra. The one and only one calculus step was this step right here, where I applied the power rule for u-substitution. And so now this 2 and that 2 are going to cancel, and when I simplify this in terms of u, I have 1/3 u to the 3/2 plus c. But now I'm not done. Be very careful. My original integral said find the integral of the square root of 2x plus 1 with respect to x. I haven't done that. I have found it with respect to u. So my last and final step is to take u home. I'm going to back substitute what I chose as the function f of x for u. And here is my answer. That is the antiderivative function for this function. When I take the derivative of this function, I'm going to get this for an answer. And you can double check that if you want to. Let's work one more example here. This is our last and final example. We'll be able to get this done by the end of the video here, and then we'll be ready to do some indefinite integral evaluations. So again, the first thing I want to do is choose u. U needs to be, most of the time, what's being operated on. So I can tell 5x cubed plus 3x minus 8 is what's being operated on. Now I'm going to completely ignore what's going on in the integrand, and I'm going to find the derivative of u with respect to x. That's 15x squared plus 3. I'm going to find the differential as opposed to the derivative, because I want du, I don't want du dx, and I'm going to completely rewrite that integrand in terms of u and du. So now I am going to take my du and I'm going to compare it with everything that's left in my integrand. Is it true that 15x squared plus 3 is equivalent to 5x squared plus 1? No, it isn't. I can factor out a 3, and what's left is what is in that original integral. So du is off from what I need it to be by a factor of 3. So I'm going to correct that by taking 1/3 of du. Now I skipped several steps where I put times 1/3 du and then factor the 1/3 out front. I just immediately go there. So now I have a simplified integral in terms of u. I picked u up, I brought it to the party. Now I'm going to find the antiderivative, 1/7 u to the 7th plus c. I can clean that up to 1 over 21 u to the 7th plus c. The very last step is I take u home. I'm going to back substitute in what the original function that I chose for u was, and there is my antiderivative function. So you can see it's much more streamlined and much more straightforward when we're not working with the theoretical functions f of x to the n times f prime of x dx. There is an exact example of what your u-substitution work is going to look like. You look at the integrand, you ask yourself what's being operated on. That's the most natural choice for you. We'll see some examples where it's not always the best choice, but it's the most natural choice for you. So then you find du. You find out if du is exactly what's left in the original integrand so that you can rewrite f prime of x times dx in terms of du. If you're off by a constant, you compensate for that by dividing by that constant out in front of your integral. Then you apply whatever technique or whatever antiderivative rule that you need to apply in terms of u. Then you can clean it up, and the very last thing you do is you take u home, because they wanted the antiderivative with respect to x. So there is your introduction to integrals, the indefinite integral most specifically. Come to class next time ready to do some homework problems.